Welcome to the Power Book of Podcasts. Unlock your potential with powerful book summaries that inspire personal growth and broaden your understanding of the world. Each week, we explore life-changing ideas, from leadership to mindset strategies to keys for happiness and success. Learn actionable insights to apply in your daily life. Join our growing community of thinkers and seekers. Like, comment, and hit that subscribe button now. It's time to supercharge your mind with the Power Book of Podcasts.
Ready to dive deep? Today, we're exploring the fabric of the cosmos. Well, excerpts from Brian Greene's book, The Fabric of the Cosmos. It tackles huge questions, physics questions, like warp spacetime, quantum entanglement, even hidden dimensions.
The cool thing about Greene is he doesn't shy away from the complexity, but he somehow makes these mind-boggling ideas understandable.
Yeah, that's what we're doing today, pulling out the most fascinating things from the book and giving you, well, like a shortcut to understanding these big concepts.
It's not just theoretical. I mean, these ideas, they change how we understand the universe, our place in it.
So Greene starts off with something pretty familiar: classical physics, Newton's laws, gravity, high school stuff, you know.
And for a long time, those laws, they worked really well. I mean, explaining the world, they worked perfectly. From predicting how planets move to understanding, well, how things move right here.
But then cracks started to show. Like, scientists started looking at more extreme stuff, like the gravity of a black hole or tiny particles. And suddenly, classical physics, it wasn't enough.
It's like using a street map to navigate the ocean. You need different tools for that.
So where did the cracks first show up? Greene uses a simple example: a spinning bucket of water, to show a problem with Newton's idea of absolute space.
Right. Newton thought the water curving up the sides, that meant it was spinning relative to this, well, this invisible grid, absolute space. But imagine, what if there were no stars, no galaxies, nothing else? Would that bucket still be spinning?
That question, it really bothered this physicist, Ernst Mach, and his ideas, they really influenced Einstein.
Mach thought maybe it's all the distant stuff in the universe, all those stars and galaxies, that actually defines motion. Like, even in an empty universe, the bucket would still curve because it's accelerating relative to all that matter, you know.
So the universe itself, it's like the framework for motion. That's a pretty big change in thinking.
It is. And it led to Einstein's theory of special relativity, which changed everything.
Yeah.
I mean, how we understand space and time.
One of the main things about special relativity is that the speed of light, it's constant for everyone, no matter how fast they're moving. Like, if you're on a train going 100 miles per hour and throw a ball forward at 20 miles per hour, someone on the platform, they'd see it moving at 120.
Right. But with light, it's different. If that train had a headlight and you were going half the speed of light, the light beam, it wouldn't be moving away from you at half the speed of light. It'd still be going the full speed of light.
Hold on. That sounds impossible. How can that be?
Because how we think about speed, it doesn't work at those speeds. Einstein realized that to make the speed of light constant space and time, how we measure them, they have to change, depending on our motion, you see.
So space and time, they aren't absolute, they're relative.
Exactly. And that's how we get space-time, this four-dimensional thing, space and time together.
And everyone's heard that equation, E, mc iota. From special relativity, what's it actually mean, simply put?
Basically, it means energy and mass are like two sides of the same coin. You can change energy into mass and mass into energy. And it tells us even a little bit of mass, it's a lot of energy.
That's why nuclear reactions, they're so powerful. They change a tiny bit of mass into energy. But how does this tie back to space-time?
Well, special relativity shows us that space-time, it's not just sitting there. It can be warped, curved by matter and energy. And that warping, that's what we feel is gravity.
So instead of gravity pulling things together, it's like things are following the curves in space-time made by massive objects.
Think of a trampoline. You put a bowling ball in the middle, it makes a dip. A marble will roll around that dip.
So planets orbit stars not because they're being pulled, but because they're following the shape of space-time, warped by the star's mass. Wow.
And it's even crazier. The warping, it affects time too. Time gets stretched or squeezed depending on the gravity.
So a clock near a black hole, it would be slower than a clock on Earth because time itself is different there.
That's right. And that's just the beginning of the weirdness of space-time.
So Einstein changed how we think about gravity and space-time. But things get even weirder with quantum mechanics, right?
Oh yeah, this is where it gets really strange, even for physicists.
So what's the big difference between classical physics and quantum mechanics?
Classical physics, it's all about knowing for sure. If you know how a system starts, you can predict what happens next. Perfectly. But quantum mechanics, It says, nope, not so fast.
So instead of knowing for sure, we get probabilities.
Exactly. In the quantum world, it's all fuzzy. We can only talk about the chance of a particle being somewhere or having a certain momentum.
And this fuzziness, it leads to some crazy stuff, like quantum entanglement. Even Einstein, he had trouble with that one. Spooky action at a distance, he called it.
Yeah. It's this idea that two particles, they can be linked, and they affect each other instantly. Doesn't matter how far apart they are. If you measure one, boom, you know about the other one, even if they're light years away.
So it's like they're talking faster than light, but that's impossible, right? According to special relativity.
Well, it's not really talking, like sending a message. It's more like they're part of the same thing, even when they're far apart.
I'm trying to get this. Can you give me an example? A real world one.
Okay, imagine two electrons. They're entangled, one spinning up, the other down. But we don't know which is which until we look.
Okay, so if I measure one and it's spinning up.
Then you instantly know the other one, it has to be spinning down.
Yeah.
Even if it's like across the galaxy.
That's crazy. How does that even work? Is there something going between them?
Nope, that's the thing. There's no signal, no message. It's like they're connected, but outside of space and time somehow.
That's hard to imagine. It changes how we think about reality, doesn't it?
It does. For years, physicists argued, is this real? Or just some math trick? But experiments show it's real. It happens.
So what does it mean? Can we use this to talk faster than light?
Not really. You can't control what you measure. It's random. So no sending messages that way.
Okay, no faster than light messages. But it still has to be important, right? This entanglement.
Absolutely. It's huge in quantum computing. You could use entangled particles to do calculations in ways normal computers can't.
So it's not just a theory. It could change technology.
Totally. And it changes how we understand reality itself. Deep stuff.
Speaking of reality, Greene talks about the universe's beginning too. The Big Bang and cosmic inflation. Remind us, what's the Big Bang all about?
It's the idea that the universe, it started super hot, super dense about 13.8 billion years ago. Then it expanded, cooled down, became what we see today.
And we have proof, right? Like the cosmic microwave background radiation, that faint glow from the Big Bang, everywhere we look.
Exactly. But the standard Big Bang, it couldn't explain everything. Like, why is the universe so uniform? Why is the temperature of that background radiation so smooth? Everywhere.
Yeah, if it started from this tiny hot point, wouldn't it be more uneven?
Right, like dropping ink in a pool, but the ink spreads perfectly evenly, instantly. Doesn't really make sense.
So how'd they solve that?
That's where cosmic inflation comes in.
Yeah.
This theory, it says right after the Big Bang, the universe expanded super fast, like crazy fast.
Super fast. How fast are we talking?
Faster than light. Now that might sound wrong, but it's not. Space itself expanding, it's different. Not limited by light speed.
Okay, so the universe blew up like a balloon during this inflation.
Yeah, and that smoothed out any uneven temperatures, stretched space so much that parts that were close became incredibly far apart.
So that's why the background radiation looks so smooth. Those faraway parts that were connected once had the same temperature before inflation pulled them apart.
Exactly. And inflation, it helps explain how the universe is structured, the big stuff. Those tiny quantum fluctuations in the beginning, stretched out by inflation, they became the seeds for galaxies, clusters of galaxies.
So the beginning of everything we see, galaxies, stars, planets, us, all from these tiny fluctuations blown up by cosmic inflation.
It's mind-blowing, right? And we even have some evidence that inflation happened. It's not just an idea.
Really? How do we know?
Well, inflation predicts certain patterns in that background radiation. And we've seen those patterns with satellites like WMAP, Planck.
So it's not just theory, there's actual proof.
Pretty much.
Yeah.
Of course, we're still refining it, testing it, like any scientific theory.
Right.
But for now, it's the best explanation we've got.
And there's more, right? Dark matter and dark energy. More mysteries.
Yep. We talked about how matter warps space-time, makes gravity. But looking at galaxies, it seems like there's way more gravity than we can explain. Like there's this invisible stuff holding the universe together. We call it dark matter.
Invisible stuff, like a whole other universe we can't see or touch.
Not a separate universe, no. It's more like a different kind of matter. Doesn't interact with light or any kind of light-like stuff. We only know it's there because of its gravity.
And dark energy, what's that?
That's even weirder. It's like this energy built into space itself. And it's making the universe's expansion speed up.
Speed up? I thought gravity was slowing it down.
That's what everyone thought, until the late 90s. Then we saw these distant exploding stars, supernovae. And they showed the expansion's getting faster.
So gravity's losing and this dark energy's taking over.
Kind of like that, yeah. And we have no clue what it is, where it comes from.
So dark matter, holding galaxies together, dark energy, pushing everything apart. It seems like the more we know, the less we understand.
That's science, always searching. And just when you think you get it, bam, something new pops up. Changes everything, makes you ask more questions.
Okay, so we've explored Einstein's crazy ideas about space-time, and we went deep into quantum mechanics, that bizarre world. But can we bring those two together? I mean, they seem so different. That's where string theory comes in, right?
Exactly. String theory. It tries to create this one big framework
Yeah.
to explain all the forces and all the particles, everything in the universe, including gravity. That one's always been a troublemaker.
So what's the idea? What are these strings anyway?
It says, at the most basic level, the tiniest things, they're not particles like little points. They're these tiny vibrating strings. Strings of energy, really.
So no more electrons, quarks, all those, just strings. Are they like guitar strings, violin strings?
That's a good way to think about it. Like a guitar string, different vibrations make different notes, right? These strings, their vibrations make the different particles and forces we see.
So an electron is like a string vibrating one way, a photon another way, and so on.
Exactly. And the cool thing is, string theory, it just includes gravity naturally. One of the ways those strings can vibrate, it makes the graviton. That's the particle people think carries gravity.
So this could unify general relativity, that's about gravity, with quantum mechanics. The other forces, that's huge if it works.
It would be huge.
Sure.
That's what physicists have been after for, well, forever. But there's a catch. To make the math work, string theory needs something really strange, extra dimensions.
Wait, extra dimensions? I thought we had 3 plus time.
That's what we see, yeah. But string theory says there could be 6, maybe 7 more spatial dimensions, all curled up, tiny, at every point in space. Too small to see.
Okay, hold on. How can a dimension be curled up, hidden like that?
Imagine a garden hose, stretched across, say, a canyon. Far away, it looks like a line, one dimension. But an ant on the hose, it sees 2 dimensions. It can walk along, but also around the hose.
So the hose's roundness, that's like an extra dimension. We don't see it from far away.
Yeah, kind of like that. String theory says maybe space-time itself is like that. These tiny extra dimensions everywhere, but we can't see them.
But even though they're hidden, they'd still affect the strings, right? And so how particles and forces work.
Right, and those extra dimensions, they might explain why gravity's so weak compared to the other forces, I mean.
Because it's like leaking into those other dimensions, spreading its force out.
Exactly. Crazy idea. But it might solve the big mystery in physics, why gravity's such a wimp.
So string theory, it's this big, ambitious idea, wants to explain everything, but do we have any proof? Can we test it?
That's the hard part. Those strings, they're super tiny, way smaller than an atom's nucleus. We don't have the tech to see them directly, yet.
So it's more of a thought experiment for now.
For now, yeah. But it's still valuable. I mean, string theory has led to some really deep math. And it connects to other areas of physics, too. Black holes, condensed matter, stuff like that.
So even without direct proof, it's pushing our understanding, giving us new ideas.
Absolutely. And who knows, maybe someday we'll have the tech to see those tiny strings.
Yeah.
Then we can really test it.
Now, that would be amazing. But we have to talk about another crazy idea, the holographic principle. Greene talks about it in the book. What's that all about?
It says, get this, the information about a space, it might be encoded on the edge of that space, like a 3D image, but the information's on a flat surface.
Like a hologram. We see 3D, but it's really stored on a 2D surface.
Exactly. It's saying our 3 dimensions, they might be an illusion. Reality might be, well, holographic.
Whoa, that's a lot to process. Is there any evidence for that?
It's very speculative. But there's some math. From studying black holes, string theory too, it seems like the information black hole holds, it depends on its surface area, not its volume. That's what you'd expect if the holographic principle is true.
So what does this mean for us? If it's true, I mean. Is our reality just a projection?
That's a deep question. Philosophically, I mean. Physicists are still working on that one. It makes us rethink space, time, information, everything.
This whole deep dive, it's been a wild ride. Warped space-time, quantum entanglement, string theory, the holographic principle. The universe is way stranger than we could imagine.
Right. And the more we learn, the more we realize how much we don't know. But that's the fun part. That's what keeps us going.
I agree. We just scratched the surface here. But hopefully this gives you a taste of the amazing things out there, the discoveries waiting to be made. In physics, I mean.
And hey, maybe one of you listening will make the next big discovery. Until then, keep asking questions, keep exploring, never stop being curious about the universe and our place in it.